Good morning. In the last class, we have discussed Hamiltonian Lagrangian formulation, and now we are going to discuss Hamiltonian formulation. Next week, we are having direct classes. You are coming to the college, therefore, this may be the last online class. I don't know exactly. Anyhow, we can study Hamiltonian formulation. And first of all, we have to discuss what are the difference between Hamiltonian and Lagrangian formulations. In Lagrangian formulation, we have already said that it is applied in configuration space. It is applied in configuration space. There is a 3n dimensional space. It is a 3n dimensional space, and the variables are, the important variable is qj, generalized coordinate, and there may be its derivative qj dot. It is also a variable, but it is a dependent variable, and t. These are the variables of Lagrangian formulation: qj dot and t. Here qj is the independent variable, qj dot is the dependent variable. Qj dot is the velocity component that depends on generalized coordinate. Therefore, it is an independent variable and a time. If it depends on time, there is time also. And Lagrangian is expressed as L is equal to T minus V. T is the kinetic energy and V is the potential energy. In the case of Hamiltonian, L is represented as T plus V. It is also an equation of motion. Sometimes it is equal to total energy. It is equal to T plus V. It has the dimensions of energy, as in the case of Lagrangian also. Hamiltonian. And the variables are, here there is a new variable. Qj is the generalized position, generalized coordinate, and a new variable is there, Pj and T. Pj is called generalized momentum. Generalized momentum coordinate. It is an independent variable. It is the main difference. It is an independent variable, therefore the Hamiltonian is applied in another space, not in configuration space. It is applied in phase space. Phase space is a 6n dimensional space. It is a 6n dimensional space. There are 3n position coordinates and 3n momentum coordinates. Momentum coordinates, generalized momentum or conjugate momentum. It is called generalized momentum or conjugate momentum, Pj. And what is Pj? Pj can be expressed just like this. That is generalized momentum consider the equation: momentum is equal to m into x dot. General equation: momentum is equal to m into v or m into x dot, and kinetic energy T is equal to half mv square or half mx dot square. Therefore, differentiating this one, we get dt by dx is equal to, or dt is equal to, dt by dx dot is equal to, with respect to x dot, when differentiating we get half into 2 into mx dot. Okay, with respect to x dot, while differentiating we get mx dot, that is equal to p. Then what is dv by dx dot? Potential energy. By differentiating potential energy with respect to x dot, this is equal to 0 because potential energy is velocity independent. It is depending only on coordinate. It is coordinate dependent and velocity independent. Therefore, dv by dx is equal to x dot is equal to 0. That is L is equal to T minus V. dl is equal to dl by dx dot is equal to dt by dx dot minus dv by dx dot, and dv by dx dot is equal to 0. That is, therefore dl by dx dot is equal to dt by dx dot, that is equal to p. That is dl by dx dot is equal to p, or dl by d, for the jth component we can write dl by dxj dot is equal to pj, or in general we can write dl by dqj dot. Pj is equal to dl by dqj dot. This is the expression for generalized momentum. Pj is equal to dl by dqj dot. And in a similar manner we can differentiate Pj with respect to x. We can differentiate L with respect to x. Here we have differentiating with respect to x dot. If we are differentiating with respect to x, we get dl by dx or dl by dqj is equal to pj dot. That is, we are getting mx double dot. Therefore, another equation is pj dot is equal to dl by dl, or we can write the partial differentiation dou L by dou qj here. Here dou L by dou qj. These are the two equations related with generalized momentum. Pj is equal to dou L by dou qj dot. Pj dot is equal to dou L by dou qj. Now we are going to derive Hamiltonian equations. We know the relation connecting Hamiltonian and Lagrangian is that the relation connecting Hamiltonian and Lagrangian, or the equation of Hamiltonian, is H is equal to sigma j pj qj dot minus L, where j is equal to 1, 2, 3, 4, etc. Therefore, we can write H is equal to sigma j pj qj dot minus L. Now, differentiate this equation on both sides. We get these equations. We can write here pj is equal to dou L by dou qj dot. Pj dot is equal to dou L by dou qj. This is the equations we have to substitute in this derivation. Now we write dh is equal to differential of this one, sigma j pj dqj dot plus sigma j qj dot dpj minus dl. Okay. Now what is h? H is a function of qj, pj and t. And what is L? L is a function of qj dot t. Therefore, we can differentiate h with respect to qj, pj and t. Therefore, we get dh is equal to sigma j is common for all, dou h by dou qj into dqj plus dou h by dou pj into dpj plus dou h by dou t into dt. Now coming to the right hand side, this is equal to sigma j, these two terms we can write just like that, pj dqj dot plus sigma j qj dot dpj minus sigma j, what is dl? dl is equal to dou L by dou qj into dqj plus dou L by dou qj dot into dqj dot plus dou L by dou t. These are the equation when differentiating the above equation both sides. Now we have to combine similar equations on both sides. Before that, dou L by dou qj dot, this dou L by dou qj dot can be written as pj. Okay, dou L by dou qj dot is written as pj, and dou L by dou qj can be written as pj dot. Now we can add similar terms on both sides. Here the coefficient is dqj, here the coefficient is dqj. These two can be added together. Now we can write left hand side, left sigma j dou h by dou qj into dqj. This is negative, therefore it is taken as positive on the left side, plus pj dot into dqj. Okay, one term. Another term, now we can erase this one. This is substituted. These two terms has taken to left hand side. Next, the coefficient of dpj here, coefficient of dpj here. These two can be combined. That is plus dou h by dou pj. This is negative, therefore this can be taken as positive, plus qj dot into dpj. Dou h by dou pj into dpj minus, this is negative, minus sigma j qj dot dpj. Now the remaining are pj dqj dot, here left hand side minus pj qj dqj dot, they are getting cancelled. The remaining terms are dou h by dou t into dt plus dou h by dou t into dt plus negative becomes positive, dou L by dou t into dt. Dou L by dou t into dt is equal to 0. Okay. Now each term in the bracket separately vanishes. Each term in the bracket separately vanishes. Therefore, dou h by dou qj is equal to minus pj dot. This term is equal to 0. Dou h by dou pj is equal to qj dot. Dou h by dou t is equal to minus dou L by dou t. These are the three equations of Hamiltonian. These are the Hamilton's equations of motion. These are the Hamilton's equations of motion, and by using these three equations we can we can solve the problems in mechanics. These are the Hamilton's equations of motion. Dou h by dou qj is equal to minus pj, dou h by dou pj is equal to qj dot, dou h by dou qj dot, I think, isn't it? Pj is equal to minus dou h by dou qj dot. We can write just like this. Negative can be taken to this side. Pj is equal to minus dou h by dou qj dot. Qj dot is equal to dou h by dou pj, and dou h by dou t is equal to minus dou L by dou t. These are the three equations of these are the Hamilton's equations of motion. Okay, using these three equations we can solve the problems in mechanics. And why we are using Hamiltonian over Lagrangian? There are some advantages for Hamiltonian because it is used in phase space. Therefore, it is easy to locate the position or motion of particles. Because we are using the independent variable. Here there are 6n independent variables. There are 3n pj's and 3n qj's. Therefore, it is more easy to locate or solve the problems. And Hamiltonian is applied in phase space. Lagrangian is applied in configuration space. That is another difference. And Hamiltonian is equal to total energy. Hamiltonian H is equal to total energy. Hamiltonian H is equal to T plus V. It is considered as total energy in certain cases, that is when the system is conserved. Only when the system is conserved, Hamiltonian is equal to total energy. Otherwise, it is only the equation of motion. The total energy is Hamiltonian is conserved when it is when the kinetic energy is velocity dependent and potential energy is velocity independent. When potential energy is velocity independent and it is depending only on position vector, then the system is said to be conserved. When the system is conserved, there are certain other conditions also. When the system is conserved, Hamiltonian is equal to total energy. Otherwise, Hamiltonian can be considered as Hamiltonian is equal to sigma pj qj dot minus L. This is the general equation. If it is conserved, we can write this specifically this equation T plus V, where T is the kinetic energy and V is the potential energy. That's all for today. We can continue in the next class. We can solve some examples or applications of Hamiltonian and equations of motion, and we can get the idea much more clear. Okay.